it can be in this particular. In particular, it can be in this particular state, where system A can be in 0, system B can be in 1, or vice versa. System A in 1 or system B in 0. Okay, this is a superposition. And this is so superposition in the context of more than one particle system will lead to what we call entanglement.
Hello.
So now we can define this entanglement in a formal manner. So suppose you have a system consists of two subsystems A and B. Now, if you can write the state psi, if you cannot write a state psi as a direct product of chi and eta, so system A is in a state chi, system B in some state eta. If you cannot write your psi AB like this, then you say system is an entanglement. So otherwise, so this is called, if you cannot, if this is not, suppose you can write as equal to here, then it will be a separable state. That is, you can rewrite the state as if system A is in a state psi and system B in a state eta. Okay. So as you know that Einstein famously called entanglement actually, as we have seen, sometimes entanglement. Okay. So now this may appear very simple definition, right? But as you go beyond 2-qubit system in a pure phenomena. Okay, this phenomena can become actually very complex. As you go beyond 2-qubit pure state system in a pure state, as you go to mixed state, or you go to even 3-qubit system, okay, you will find this entanglement is not as well understood as you would like. Okay. So even as soon as you go beyond very simple system in a very simple state, phenomena of entanglement, is still not well understood. Okay, so here is a very simple example. Okay, so one thing is clear that an entangled state is a superposed state, right? But all states which may appear to be superposed may not be actually entangled if we choose an appropriate basis. Okay, so we may find if we change the basis, then state actually is in a product state. And very simple example is here. So you have a naive superposition of 0, 1, 1, 0, 0, 0. But you may think it is in some vague sense maximally entangled also, but you can always change the basis and you will find that this state can be rewritten in terms of system A being plus as well as system B being plus state. Okay. So even whether a state is entangled or not, when it is given to you, often it is not very easy to say whether a state is entangled. There are ways to do it up to 2 qubit. As soon as you go beyond it, it becomes very hard. Now, most famous 2 qubit entangled states are called Bell states. As most of you know, there is psi plus minus 0, 1 plus minus 1, 0, 5 plus minus 0, 0, 1. So these are the 4 Bell states. They also form a basis for a system of 2 qubits. Okay. So often you will hear about making a measurement in Bell basis. So this is a basis which you use to make measurement. Okay. So now we are, so as of now, we have what you may say undergoing second quantum revolution. So what this revolution is basically about? This is about using entanglement. Okay, so now once you know entanglement might be important, then you can ask many questions. Given a state, can we quantify the entanglement? Which entangled state is more useful for a given task? Can we say that a state is more entangled than the other? Then if a state is more entangled, is it more useful? Answer to all these questions can be very complex as soon as you go beyond system, which is a 2 qubit system as a nuclear state. Also answer will depend on many things. Is it pure state or mixed state? Is bipartite, multipartite? Do we have qubits or high dimension? But everywhere we still have lots of unanswered questions. But this revolution is not about so much understanding entanglement. It is more about using it as a resource to do things which were not possible until now. Well, until maybe 2-3 decades ago. Okay, so one of the things which makes quantum mechanics weird goes under the name of non-locality. Okay, so this is about foundation part. So actually, you may say second quantum revolution started with a foundational question. So you know these, you may have heard about something called EPR paradox. Einstein, Podolsky, and Rosen, they wrote a paper in 1935, and they asked a foundational question. Can a quantum mechanical description of physical reality can be considered complete? So they had no interest in applications, okay? But this question, after 50 years, led to what you may say second quantum revolution. So asking questions which may not have immediate experimental relevance can be very important. Okay, so let me go over a bit, which means this slide may seem a bit abstruse, but then we'll see a specific example where things will be more clear. Okay, so it is a superposition and its manifestation as entanglement for composite systems, which give rise to many enduring mysteries about quantum mechanics. And the EPR paradox actually it illustrates it. So this paradox has 3 parts: notion of realism, notion of locality, and notion of completeness. So first, so these are all statements from that paper. Okay. So this paper introduced something called realism as follows. So suppose now you have 2 systems. If without any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Basically, it means that system has some innate properties to which this physical quantity corresponds to. Then notion of locality is easier to understand. Basically, it tells you that these elements of physical reality belonging to one system cannot be affected by measurement performed on another system, which is spatially separated from the power. Okay, and then they have a condition of completeness. A necessary condition for a theory to be complete is that every element of physical reality must have a counterpart in the theory. If it looks a bit confusing, things will be more clear if we look at the example, which was in the paper of EPR. So what did they do?
they analyzed a particular state of two particles involving position and momentum in one direction. And then they argued that that quantum theory is incomplete. So, I mean, this slide will give you make things more clear. So what did they do? They considered the case when two quantum systems interacted. So you see, if you want to create entanglement, systems have to interact at some point, right? So this is, so suppose you have a two quantum system which interacted at some point, okay, in such a way that their spatial coordinate and their linear momentum, they become coupled, okay, and they remain coupled even when they become widely separated. So they wrote down this wave function, okay. So you have a two distant particles. This is a wave function. Say position of one particle is x1, second is x2. This is some L, okay, which tells you the how far apart these particles are, and P1 plus P2. Okay. Here you see the delta function as representing some normalized function with arbitrary high and narrow peak. Okay. This wave function represents two particles at relatively large distance, which is close to L, and their total momentum is arbitrarily close to 0. Now these operator x1 minus x2 and p1 plus p2 commute, so system as a whole can have the values for this x1 minus x2 and p1 plus p2. Okay, now suppose we don't know the position or momentum of the individual particles, but suppose we measure the position of particle number 1 and we get the value x1. Then we can immediately predict the value of x2 without disturbing it. Okay. So I make a measurement on particle 1, I see its position is x1. Then for this wave function, I can immediately predict the position of particle 2 without any way disturbing it, right? So we may say there exists an element of reality corresponding to x2 for the particle 2. Similar, okay. So they argued since at the time of measurement, two systems no longer interact, no real change can take place in the second system in consequence of anything that may be done to the first system. Right? This is locality, right? Therefore, observable x2 correspond to an element of physical reality. Now, similarly, you can measure P1 instead of x1. Then again, suppose you get a value P2, then you immediately know the value of P2 for the system 2. So what it tells you that you can find out value of x2 on the position and moment of particle 2 without disturbing it at all, right? So it means their values for x and p exist for particle 2. But quantum mechanics precludes the simultaneous assignment of precise value to x2 and p2 because they don't come out, right? So now here is then contradiction, right? If we go by the assumption of EPR, then it appears there should be simultaneous value of x and p for particle 2. But quantum mechanics tells you that it is not possible. So conclusion of EPR was that quantum mechanical description of physical reality given by wave function is not complete. So in this incompatibility, they drew a conclusion that is a quantum mechanics is incomplete. Later, the work by Bell suggested otherwise. Okay. But they left the door open. Okay, what might be a more complete description. So that's why we have lots of interpretation, lots of extensions. Okay, so what we have seen, a foundational question was asked by EPR, and that led them to conclude that perhaps quantum mechanics is incomplete. You need a deeper theory. Okay, but it was a foundational question, so it remained as such. Okay, some people took them seriously, some people ignored it. Okay, because it was of no immediate practical consequence. Okay, it was just a philosophical question. So this EPR paper prompted Schrödinger to introduce two terms. One is, okay, it was in German. If you loosely translate, it is translated to entangled state. Okay. He also introduced another notion of steering, which is sort of set of steerable states are their subset of entangled state. Okay. So entanglement is a characteristic trait of quantum mechanics, one that enforces its entire departure from classical line of thought. Okay, these notions remained dormant for almost 25 years until Bell in 1964 actually introduced an inequality which can test whether Einstein's notion of local realism was valid or whether quantum mechanics was incomplete. So he wanted a test, right? And Bell provided such a test. But in 64, this all this discussion about foundations were not very popular. So he published his paper in an obscure journal called Physics at that time. This is John Bell, in 1982. Okay, it has become more fashionable as compared to when he introduced Bell inequality. So he could speak about it sort of freely. Okay. So this Bell inequality, so John Bell, as I said, in 1964, in a seminal work, gave this, Bell's theorem, which was published in some obscure journal. Okay. So in 1969, actually, there a paper came which gave another version of this Bell inequality, and that was tested in 1972 by Friedman and Clauser. Clauser was a postdoc and Friedman was a student, okay, at that time. And Clauser was astronomy, but he somehow persuaded his advisor to allow him to pursue his passion to test Bell. And actually, he thought that he will prove Einstein right. But it turned out the other way. Okay, so in 1972, they published their results. Okay, so then John Bell, once your work has people experimentally testing, then you become, more comfortable talking about it. So as Clauser said that at that time that foundation had never discussed, okay, quantum mechanics foundation was not a topic at that time. So Bell in the originally proposed a Bell inequality which had three observations. This Clauser et al. They generalized it to two independent measurements. So okay, so what is it? Okay, so here let's just look at it slightly closely. So you have a system of two particles. One is possessed by what people call Alice, and other is possessed by what is called Bob. So Alice and Bob, they are these, instead of saying system A and system B, it is now more borrowing the language from cryptography. Use this, we use this Alice and Bob. So you have two particles, Alice and Bob. They have one particle each, and these two particles are in an entangled state. Okay. Now Alice has a particle. She can make a measurement of two observables, A1 and A2. Similarly, Bob can make a measurement of two observables, B1 and B2. Okay, so this is one of the scenarios which was considered by Horn, Shimoni, and Holt. Okay, maybe in passing I should mention that at the time, Clauser made a measurement and showed that Bell inequality is indeed violated. Horn did another experiment where he actually found that Einstein was correct. Okay, so there was but people repeat of Horn. So there was a contradictory experiment. Okay, but then experiment could be verified while other could not be. Okay. So here, and when we say these are observables, they need not be within quantum mechanics framework. Okay. So they wrote just as a combination of these observables. So A1 and A2 are measured by Alice on her particle, and B1 and B2 are measured by Bob on his particle. Then they made this combination, A1, B1 plus B2 plus A2, B1 minus B2. Now here we see in action what we say notion of local realism, because if you use that, then you will find that if you make a measurement on a number of such systems in identical state, you will find that average value is less than or equal to 2. This is what is Bell inequality. So what you see here is the following.
Now we assume that A1 and A2 can have independent value. Okay, that if it is not the value of A2 depends on the value of A2. Okay, where you have this real. Okay, that value of A1 and A2 can be independent of each other. Similarly, value measured by Bob for B1 and B2, they are independent of the values obtained by Alice. So that is, so it means you allow A1, A2, B1 and B2 to take all possible +1 and -1. Okay, so you have a locality as well as a realism. Okay, locality means A1, A2, they don't depend on B1, B2 values. Realism means B1 and B2, they are independent of each other, similarly for A1 and A2. Then since value can be +1 and -1, average is easily. So here suppose B1 and B2 have identical, I mean they have either +1 and -1, then this term will be 0 and this can will give you 2 or -2 and vice versa. So average will be less than 2. So this is what is the inequality. Now question is whether quantum mechanics violate it. Okay. Okay, so now remember, now we want to come to quantum mechanics, right? So this A1, A2 and B1, B2, they are some kind of Hermitian operators, right? We want to see what quantum mechanics is going to predict, okay? So we have to make some choices for A1, A2 and B1, B2, which are the observables used by Alice. Let's come here. So this is a particular choice. Okay. So let's take that Alice is measuring either the polarization along x-axis or y-axis, while Bob is measuring along these particular variable B1 and B2. Now once you know the operators, right? So I can go back, substitute those operators here and calculate the expectation value. Okay. Now to calculate expectation value, I need a state. So actually it can be shown that if you have a 2-qubit pure state, by using something called Schmidt decomposition, you can always write that state in this form. That is C0, 0, 0 plus C1, 1. Okay. Now here 0 and 1, they are the eigenstates of sigma z. Okay. So now if I calculate this expectation value, I will find this thing 2 root 2 into C, where C is basically 2 C0, C1, where C0 and C1 these are coefficient. You immediately see if state is not entangled, it means one of them is 0, then this expectation value is 0 and it satisfies the Bell inequality. Okay, but still here if you see that if value of C is less than 1 over root 2, then again Bell inequality is not violated, right? So this expectation value depends on your measurement setting, right? Your measurement setting means what are the observables that you are going to measure. Okay, but it has been shown there exist sets of measurements, okay, which depend on the values of C0 and C1. So A1, A2 are like sigma Z, sigma X, but B1 and B2 they depend on the value of C0 and C1 in that state, right? C remember is 2 C0, C1, and C0, C1 are this what people call Schmidt coefficients. Okay, so I'm choosing my angle which depends on the state. If I do that, then I again calculate this expectation value. I will value 2 into 1 plus C square. So which is concurrence. So here what you see immediately, if C is more than if it is not equal to 0, then this value is more than 2, which is a violation of Bell inequality. So as soon as this state is entangled, howsoever small might be the entanglement, you will have a Bell violation. Because then as C square is positive, and this will be more than 2 as soon as C is non-zero. Okay. So what you see here, goes under the name of Distance theorem, that every pure entangled state violates this Lipschitz inequality. Now this is very simple starting point of this whole non-locality game, which took place
many decades ago. Nowadays, you can go beyond 2 qubits, pure state, you can go to multi-parity state, you can go to mixed state, and there are lots of Bell inequalities. So lots of people work in it. In India also, we work on this field. Okay, our group has also worked. Okay, so this is just the starting point. A non-locality for 2 qubit system, which is the simplest case we could have. Anything beyond it, things become actually more complex. And there are lots of questions that are still unanswered. Okay. Okay. So as I just mentioned a while ago, in this Bell inequality test have been going on for more than 50 years. As you know, we saw 1969, or 1972, Clauser and Friedman published their results. But there are certain loopholes which people kept questioning, okay? And there are certain assumptions, which go in deriving those Bell inequality, whether they are being verified, they are being satisfied by your experimental setup or not. Okay, well, locality loophole and in detector efficiency loophole, they were the two main loopholes. In 2015, there were 3 groups which reported experiment which seem to have closed this loophole. So what it tells you that indeed Einstein, we can't, this question which was raised whether quantum mechanics is complete or not, and its alternative if you take, they are not true. Okay, so it is quantum mechanics is in some sense complete. Okay, you cannot find a local version of quantum mechanics. Okay, so Clauser once said he was a bit sad when he showed that Einstein was not right. Okay, and he started out to show that Einstein was right. And of course, after Clauser, Aspect, and Zellinger, they made further improvement in this testing of Bell inequality, and they got Nobel Prize. Okay, so as this thing I already told you, it started when Clauser was a postdoc at UC Berkeley, and at that time this inequality was not fashionable. But important point for the students is that although he had a passion, he wanted to show Einstein was correct. Okay, so he persisted in trying to work on an experiment which was not fashionable. People were not interested whether Bell inequality is violated or not. So it have affected his future job prospects. But he had a passion. He was interested in showing something specific, and he persuaded his postdoc advisor that he may be allowed to work on on this not fashionable topic rather than on the topic for which he was hired, which was to work in radio astronomy. And his advisor also allowed him to do it and assigned a student, Friedman, and they worked together and showed something for which he got a Nobel Prize after so. So lesson is being here that follow your passion. So whatever you think you find interesting, even if people around you tell you, okay, no, it is nobody likes this topic and all that. But if you find that line of thought interesting, okay, so this was foundation, and what they used subsequently, this entangled states were used for quantum communication apart from quantum computing. Okay, so it was actually quantum communication which first made this quantum information very popular topic. So it started with this phenomena of what people call teleportation. Okay, which was in early 90s. This phenomenon was shown, and ever since then, people started this entanglement more seriously from the application point of view. Okay, so there are many tasks that one can carry out with the assistance of entanglement. Okay, some of these tasks are only possible with quantum. A study of this entanglement took off with the introduction of many communication protocols, and possibility of more powerful algorithm for some computing. I mean, this quantum computing algorithm also came in 90s, the Shor algorithm and all that, okay? And okay, so in communication protocol, what happens? It means you want to communicate something. What do you want to communicate? Something classical or something quantum, right? So you may want to communicate some classical information from A to B or A to many parties, or you may want to send some quantum information. Here, this quantum information could mean a quantum state, which may contain some information. Okay. So this is what you want to do. So some of the protocol at that time in early 90s or in 90s, which were introduced were teleportation, super coding, and the entanglement swapping. So I will talk about these two because they have been referred in this Nobel Prize citation. Okay. Okay, so in most of these protocol, one party, say Alice, can communicate quantum information in the quantum or classical information to Bob either directly or with the help of one or more parties. Okay, so we'll discuss two of these protocols, which are simplest possible. Again, when these protocol, whatever discussion we will have, it will be again in a very simple context, original paper context, but there are hundreds of papers in these areas, okay, where you generalize except for a simple set of states to more complicated states. And there is still unanswered question. You see, this is what is interesting. Certain questions you may think are very simple, but then you find, oh, they don't have easy answers. Okay. So when you want to manipulate a quantum system, one other thing apart from measurement, you apply unitary operator. So more common unitary operator which you want to apply on qubit are these, this NOT gate or poly Z and Hadamard. Okay, and one of the most important gate which acts on 2 qubits goes under the name of control NOT gate. That is, you apply transformation of second qubit depending on the state of first qubit. And this, so whenever there is any application, first thing one experimentalist tries to see whether they can implement this thing, because it's part of what goes in the heading of quote unquote universal set of gates. Okay, so using this is just a very simple example here. You can create Bell states by using these gates. So for example, you start with a state which is 0, 0. So what Hadamard does, takes 0 to superposition of 0 and 1. Okay, so you start with a state 0. You apply this Hadamard gate, it will become 0 plus 1. Then you apply what is known as control NOT gate, which will change 0 to 1 if this qubit in a state 0. It will not change if this is in state 1, it will change. So it will lead to this state. Because after this, it became 0, 0 plus 0, 1. Once you applied this, this will become 0, 0 and 1. I have not explained it, but you just apply, whole idea is this will make it 0 plus 1 superposition. Then this will change the state of this qubit depending on the state of this qubit. So this is a way easy to create in at least theoretically entangled states. Okay. So in a lab, this is what you can do. If you know how to apply a Hadamard gate or how to apply a CNOT gate, you will get entangled, right? So whatever system, if you have a 2 qubits of whatever kind, if you know how to apply these 2 gates, you can create. Actually, you can, if you go to multipartite also, as long as you know how to apply these gates, you can create multipartite entangled states also. Okay, so these 2 are very important gates which all experimentalists try first time. When they have a qubit, this is what they want to do first time. Okay, so this is a presentation of this teleportation. So what happens here? What is the goal? Goal is that Alice wants to send the state of particle which she has to Bob. So idea to send quantum information. That is a state which Alice does not know. She wants to send this state to Bob. And she shares a pair of entangled states. So she has two qubits. One is entangled with Bob, other is the particle, and instead of this particle, she wants to send to Bob. Question is, can she do it? Okay. So the method which was proposed by these guys in 1993, Bennett, Burchard, and this Creque and Josa, Perez, and Wouters, actually they introduced this protocol in this very simple case. So basically, idea is that Alice wishes to send an unknown quantum state to Bob. Then one thing is she can just send the qubit, right? But if she doesn't want to send that qubit, she wants to find some alternate method to do it. So let's go to the picture, and then mathematics maybe we will ignore a bit. So this just has three. First part is Alice will make a measurement. So Alice has two particles. Now she will make a measurement on these two particles in what is known as Bell basis. As I showed you those four Bell states, use those states to make a measurement. Then result will be there will be some collapse of these two qubits in a particular state. Then Alice will use some classical information to convey the state of these qubits to Bob. Okay, after this measurement, this and this particle will become entangled, this particle will become unentangled. And the state of these two particles, Alice has to send to Bob. And remember, there are four possible Bell states, right? So there are four possible states for these two particles. So this information can be encoded in two classical bits, right? Because you have to encode four pieces of information, right? So you need two classical bits to encode these four pieces of. So once Alice sends the information to Bob, then Bob applies some local unity transformation on his qubit to convert the state of his qubit, as you see this original qubit. Okay, so three parts. Alice makes a measurement using Bell states. Then she sends the outcome of her measurement to Bob using two classical bit of information. And that information is used by Bob to convert the state of his qubit to that of Alice's. So these are just three elements in this protocol. Okay. So two classical bit of information has to be sent. And this mathematics is also very simple. Any student even at BSc level can do it. Okay. Okay. So this comes under the name of LOCC. So what Alice is doing, she's making a measurement locally on her two qubits. Then she's using classical communication to send the result of outcome of measurement to Bob. So this is we are under the heading of LOCC, local operation and classical communication. So as I was just explaining that in the original protocol, transmits unknown one qubit state using a Bell state as a resource and using two classical bit of information. Okay. Now, as I again will tell you that when you have only Bell state as a resource, and she wants to send only one qubit state, it is very simple. But as soon as you go to multipartite entangled states or mixed state as a resource, and if Alice wants to more complicated states, whole thing can become very complicated, and there is still unanswered question. Okay, so here is just simple mathematics, which I will just I will just I don't want to go to each step. Okay, main thing, as I told you, Alice wants to send this state, and they have this resource state. This is a share. Okay, and then you can so this is a combined state. You can rewrite in a simple manner, and there are four possible outcomes. These are the Bell states. Then after she makes his measurement, Bob state can be either of the four possible states. Okay, this is simple mathematics here. You just rearrange terms. Okay, so original protocol in retrospect is mathematics is not complicated. Okay, then Bob applies local transformation to convert the state of his qubit to original state of the Alice. So by summary, as I told you earlier also, Alice and Bob share a Bell state. Alice can send an unknown quantum state to Bob by making a local 2-qubit measurement and by sending 2 bits of classical information to Bob. Then Bob makes a local unitary transfer. So this is so as such is simple, but as I told you, there are hundreds of papers in this field. Many people in India, including our group, have worked on it. Okay, all over world, of course, there are hundreds of papers. But as soon as you go beyond this simple resource state, okay, and as soon as you go beyond the state you want to send, life is not always that easy. I mean, this is just an example. Suppose you want to send a more complicated state, then what do you do? Okay, then there are ways to do it. And there is a theorem which one can state, to answer some of these questions. Okay. So if you are so question, what is the basic question? I am given a n qubit state, okay, which may have n terms, okay, and I want to teleport it, right? That is, Alice may want to send that state to Bob. So question is, what kind of resource state do you need, right? To do what is a exact teleportation, which is a unit probability and unit fidelity. That is the exact state, right? And it is always, process is always successful. Of course, one can discuss this phenomena when probability is less than 1 and fidelity is also less. Fidelity means how close Bob's state is close, how close is Bob's state to the, okay. Or if you given a resource state, what are the states that you can teleport using that resource? Teleport again means exact teleportation. Okay. So the answer to this question, okay. So if Alice wishes to send an n qubit state with M to Bob, then the resource has to be distributed in such a way, then Bob's n qubit has this particular entropy. This von Neumann entropy, as most of you know, which can measure, the in a state, or in this case, you may say entanglement also, okay, but entangle only for 2-qubit pure state. But here, given any system, you can calculate entropy, okay. Okay, so given a resource state, we can compute entropy for all partitions. If something corresponds to log 2m, we know which state you can use to teleport it. Okay. Oh, so I think, okay, fine. So this is swapping, but I just want to tell you by picture also only. This is also very simple if you look only Bell state, because this is very important in quantum network. Okay, why? So what happens here? So originally you have 4 particles. So if you have a 4 qubits, you can show it actually. So you have 4 particles, 1, 2, and here AB. 1, 2 are entangled, AB are entangled. Remember, there is no entanglement between AB and 1, 2. Now suppose I make a measurement using Bell basis say on 2 and A, then what will happen? 2 and A will become entangled, which is not surprising given that you have made a measurement on 2 and 1. But what is interesting is that 1 and B, which have never interacted, they also become entangled. Right? So this swapping of entanglement between 1 and 2 and A, B to 2 and A and 1 and B. But most interesting thing about this phenomena is that particle 1 and B, which have never interacted, they become entangled when you make a measurement in 2 and 2. Okay. And this is a simple phenomenon, but it is, as I just mentioned, it is used in quantum networks, quite a lot. So we will not do the mathematics here. Okay, I think it's maybe I should ignore this. Okay, thing is, cryptography is that most of the application, which are popular, they are basically, related to quantum cryptography. So how much time will you give me? Not much, eh? 10 minutes? 5. Okay, so I think without going in detail, I will just, most of you know about it anyway, but let me just say a few. I will not go in detail here. I will ignore the details. Okay, so some of you may have heard about something called BB84, this cryptographic protocol, which was actually, given in a conference in Bangalore by this Bennett and Brassard. So basically, they didn't use entangled state. They use what you may say superposed state and transmitting of quantum system. Okay, so this protocol didn't need entanglement. But in 91, there was another protocol by Eckert where he used entangled state. So when I say quantum crypto, it means basically use QKD, quantum key generation is the main part here. Okay, so let me just say a few lines here. So okay, so what happens in a cryptography usually, simple cryptography? Goal is to communicate information by Alice to Bob without being compromised by third party, say E. So what are the main part in a simplified, protocol? So there is a message, okay, say M, then there is a key. So again, Alice to Bob, right? So Alice will use, so Alice has a message M, she will use a key K and use some what you call encryption method. Then she will convert this original message. So there are two parts, encryption method and generating this key. Using that, she will convert this original message to something called C, which is called cipher. Then what Bob will do? So then this message is sent to Bob as C. Bob will receive this message C. Then he will do decryption. He will use, okay, in what we call symmetric key, he will use the same key K, use something called decryption procedure and get the original message. So two parts, use a key, use some encryption procedure, then Bob will may use the same key or different key depending on what this cryptographic protocol is, and use some decryption procedure to convert the message that he obtained or that he received to original. Okay. So in quantum cryptography, basic thing goal is to generate this key. Rest of the thing is same. So basically in this protocol, they basically, so this is about classical, which I am ignoring. So this is, I think, only slide I will just talk about. So Alice and Bob, if they meet, they have met sometime in past, they can decide on a particular key. And then this is private key distribution. Okay. But suppose they have never met, then they have to somehow generate a key. Okay. And by, so using some public channel in some sense. Okay. And then if they are doing some communication over a public channel, it can be intercepted by some third party. So in quantum cryptography, basically you use quantum mechanical resources to generate this key in a safe manner. And this whole thing is called key distribution. So this before occurred, and now you see again, they were the initial simple protocol. Now we have many more complicated protocols. Then one want to study also their security and all that. Okay, so this also, thousands of papers are in this area, but it started with this BB84 and E91 protocols. Okay, so how this key is, generated? I mean, I think I will ignore that part because of lack of enough time. Okay, so I think I wanted to mention applications. Cryptography, many companies, okay, which are offering products based on quantum information processing. One of these company is a Swiss company, ID Quantique. Now there's similar company in US and Canada and many other countries. So on their website, you will see they have some series, which is the first comprehensive range of quantum key distribution solutions. So point being, we already have come from two applications, right? Designed for enterprise, government, and telco production environment. It provides the ultimate in quantum safe security, guaranteeing provable security key exchange for encryption. So basically to generate the key, to encode your message. Okay. So it is already here. I mean, practical things are already here. Not only that, then you also have a long distance quantum communication already. So entangled states between photon has been demonstrated over hundreds of kilometers. Okay, using optical fiber. So here are some of the headlines. Okay, So for the first time, a team has sent a light particle entangled with matter over 50 kilometer optical field, where the long distance communication is either space-based or quantum or the optical fiber. This paves the way for practical use of quantum networks and a milestone for a future quantum entanglement. Again, entanglement distribution over 96 kilometers. Then entanglement swapping has been shown over 100 kilometers using optical fiber. And of course, so these other headlines. So basically, they have shown teleportation over more than 100 kilometers. So this is using optical fiber. But nowadays, people are trying this what is known as space-based quantum connection. In 2016, China launched a satellite called Messias, which were dedicated just for quantum information science. Okay, so using this satellite, they can have communication between, say, two ground stations, which were separated by 1,000 kilometers. In 2020, they showed that you can communicate in a secure manner between two grounds which are separated by 1,000 kilometers. So they have also shown, that you can transfer a state over a distance of 1,200 kilometers. Okay, because optical fiber, beyond a distance is not a suitable, medium to use. So you have to go to space-based. So people are already showing practical application, okay, of this entangled state, right? So we have an era of this quantum communication. Okay, it is already there. So, okay, so let me just one or two slides, so in India, we are doing this catch-up game. So in 2023, April, I think 6,000 crore almost have been approved under this National Quantum Mission for about a period of 8 years. Okay, so there are four main major thrust areas: quantum computing, but also quantum communication, quantum sensing and metrology. Okay, they misprint there. And then also quantum material and devices. For these four different areas, 4 hubs will be established, which will then help, carry out research at that place as well as to help other institutes in the country. Okay. So these are the goals. Okay, they are relevant for quantum computing and quantum communication, which they want to have in next 8 years. So first they want to develop in India the quantum computer with 20 to 50 physical qubits in 3 years, 50 to 100 in 5 years, or 50 to 1,000 in 8 years. The goal is to have at least 50 physical qubits in platform, especially like superconducting, as well as for using superconducting and photonic technology. Because remember, photonic technology is very important for communication. Okay. So this is about computing part. Can we have qubits, say at least 50 qubits entangled in say 8 years? Next is about communication. Develop satellite-based secure communication between two ground stations over a range of 2,000 kilometers within India, or also, so again, secure communication, right? So using make it key and all that, okay, with other countries. Third is intercity quantum Q distribution over 2,000 kilometers with trusted nodes, okay, using existing optical fiber. They want to establish multi-node quantum network with quantum memories and all that. So this is where I think, whether in Calcutta or in Eastern India, we can have a node which is a part of this quantum network, right? Or whether, since you need only optical fiber, technology, and okay, you need other stuff also like single photon source and detectors for single photon. But can we have some Eastern India also, right? Some way to distribute key over a few hundred to start with kilometers optical fiber, okay? In India, already, I think in South India as well as Northern India, people have tried to do this, to implement this quantum cryptography protocol over, I think, few hundred kilometers using optical fiber. So I think these are the main goals from the point of view of computing and communication. Of course, there are also goals which go to this, you may say, this third focus area, which is about quantum sensing and metrology. Basically, develop very sensitive devices, okay, using quantum technology, okay, relating to magnetometer and atomic clocks. Which you want, basically you want to enhance sensitivity. The part of quantum sensing. And then, of course, under fourth thrust area, you want to develop quantum material which are more suitable for quantum communication and quantum computing. At the same time, you want to have these single photon sources and detectors, similarly entangled photon sources, and all that. So these are four thrust areas. These are four goals for those thrust areas. Okay, so here I will just conclude. So Nobel Prize in Physics in 2022 recognizes the importance of entangled systems for future technology. Experiments have proven that entanglement is very real. There have been experiments, testing this Bell inequality. People have done this teleportation, swapping, and many quantum communication protocols have been implemented. All of those protocols have entanglement. So it is real and fundamental in nature. Quantum mechanics has been now shown to work, not only at very short distance, but is communicating over thousands of kilometers, right? So quantum cryptographic systems are already available. One can look forward to more innovation by harnessing the power of entangled systems. And we can look forward to quantum communication networks. Of course, India, in using this national quantum mission, is getting ready to benefit from this new quantum realm. So I think I have finished in time.
Okay, so are there any questions?
Yes, so this itself can be a very interesting topic, okay? And no two persons may agree. But you may say information encoded in a quantum system, which you cannot codify in a classical system. So like you take a state, alpha 0 plus beta 1. So here your information is encoded in this constant alpha and beta, right? So information can be processed in ways which is not possible to process in, say, some classical manipulation. Okay. Suppose alpha and beta, this is some information you encode in some classical system. You can manipulate in some ways. Yeah, of course. I mean, right? That's whole quantum technology is about, right? Because there are information in terms of these all these coefficients, right, in a quantum system, and you can process this system using this quantum measurements and quantum evolution, applying these gates and all that, and achieve results which you cannot using this classical system. Right. So here it can be, you want to send a quantum state, say, for example, the whatever 18 ports you may say is quantum information. Okay. And if I want to send them, just say I told, I mean, actually some of this information can be manipulated more efficiently using a quantum system, or just as, for example, quantum computing, right? Whatever you can do using a quantum computer, you can do using classical, but it may take lot longer time, right? You may need bigger computer with more time, more resources, but you can do here manipulation information more efficiently. And some of the things that you can do, say for take teleportation, which I talked to you about. Here you want to send a quantum state, in some sense quantum information from it. No. So it includes some classical component also here. So what it shows to you, information cannot be transmitted with the faster than speed of light, because there is a classical communication part. So we are not, so issue is not that whether you can do faster than the speed of light. That is not the question. Question is, can you do something more efficiently and better
than using just classical. Some of the things you can always do better, and some of the things which you could do using quantum resources, you cannot do using even classical. Okay, so you have this information, what is classical information? This is a very fundamental question, and people may not agree. I think there's a talk also, I think maybe in a few days, where they will be, speaker will talk about what is quantum. And this is a question which different people may have different opinions. But in vague sense, quantum information is encoded in a quantum system. And where, in terms of all the parameters which characterize the state of that system, then you can manipulate that that state in the way you cannot manipulate a classical state. Then using that manipulation, you can achieve results which you cannot by using a classical system, which may encode the same thing. Yes. Right, right. Right. Right, right. Right, right, right. Right.
Of understanding what you are taking the law for.
Yeah.
If
Right.
quantum and there are microstates also
Right, 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 right.
here I doubt you to have it.
No, no, here we, okay. Now coming back to this question,
What is that?
okay.
Why are you using essentially the same formula?
Uh,
The base of n.
Except to that Boltzmann coefficient. Now, okay, now coming back to this question, you see, there are many, some you may say apocryphal stories. See why this is entropy related with this Boltzmann entropy. Now, sometimes you see, if you just there are two places, one may think they are related. Some people do think they are in some way related, but okay, this is just a story. I don't know how true it is. So this, as you know, this entropy, when it was introduced by Shannon, he introduced this entropy to use to characterize classical information basically. So the story goes, he asked, okay, I have this quantity, what do I call it? He asked one human. Then one human said entropy is something which no one understands, so we can call it entropy. So it is possible that there is no relation as such between the what we Boltzmann entropy and here this Shannon entropy. Okay. Entropy is for classical system, then we generalize to quantum system and we call it one entropy. So, but some people, because name are same, they do try to find some relationship between. Now, in this case, entropy, it characterizes the uncertainty in the state of a system. So, like Shannon entropy, so suppose you have some random, so it which characterize some uncertainty, in whatever that distribution is characterizing, and this quantity characterizes how much uncertain the state is. Then, if I make a measurement, that information I will get, right? Whatever is uncertain is the information that I want, right? So this characterizes the uncertainty in the state of a system. For example, if a system in a pure state, entropy 0 because I know that state. But if a state is in a mixed system, a mixed state, then the uncertainty, and I will get non-zero. So it characterizes in some sense like Shannon entropy, uncertainty, in the state of whatever, and the uncertainty is characterized by this entropy. So this is one of the measures. There can be many more measures. Sure. Sure.
I am
Right. Right.
that I right there put the probability of mixed one boundary part.
Okay, so suppose I am given a state, say quantum state, which can be pure and then the entropy is being used here. Actually, entropy is just one of the measures. I said concurrence I mentioned also. So, okay, so let's look at it. So you have a say system of say two particles, right? Now, suppose I know what the state of that particle is. So there is no answer. I know what the so I'm not doing any communication or anything. I'm just given a system in a particular state. Now I can
You know that.
I know that. Then there is no uncertainty. I know what the state is. So if I want to calculate what is known as von Neumann entropy, I will find it to be zero because uncertainty is zero. Now, if you have a state of two particles, don't know the state of individual particles. Because if you want to find out the individual state, if original state is entangled, then the state of individual particle is uncertain. Because as I said, suppose you have 0, 0, there is something to write here. Okay. So suppose I wrote this Bell state. So but we have 0, 0 plus 1, 1. This is a state of two particle. No uncertain. Okay. 0. But now I want to look at the state of particle 1. So it can be either 0 or 1 because 0, 0 plus 1, 1. If I calculate the density matrix for it, it will be half 0, 0 plus half 1, 1. Entropy will be non-zero. Because now state of particle 1 is uncertain. Right? Because it can be either 0 or 1. Now, how uncertain it is, it will depend on the coefficient of 0, 0, and 1. That is what entropy will catch. So entropy will basically log 2 of these coefficients, sum over it. Okay. So what I'm saying is entropy in some way captures the uncertainty in the state of a system. And this is just one of them. So say for example, you come to see this is a problem. If I have a quantum system, usually people use von Neumann entropy to characterize this entanglement. But if I go to a mixed state, then I have another uncertainty because of classical mixing. That also contributes to the von Neumann. So then I don't know. So then it cannot characterize the entanglement. Because now I have an uncertainty due to superposition as well as due to this classical mix. So there are two elements which are contributing to the uncertainty of a state of a particular particle. So then people don't know how to characterize, uncertainty, quantum uncertainty due to the quantum nature of that particle, because it will get mixes with the classical uncertainty. Then people do various decompositions and try to see which is more efficient. So point being, it characterizes some uncertainty in the state of a particle. If there is uncertainty, then entropy will be non-zero. Sorry, if there is uncertainty, if it is no uncertainty, it will be. It can give rise to, it depends. Different uncertainty will give rise to different fidelity for, okay, so suppose teleportation state is sent by Alice to Bob. Now question is whether Bob's state is close to the state of Alice. That is a fidelity, that will tell you. Now the resource state, depending on different entanglement, will give you different fidelity. Okay, so suppose so in that way, uncertainty in the state. So now different coefficient mean different uncertainty. In that way, that uncertainty will affect the fidelity. So your research state. Yeah, right. Right. And that strength will tell you how uncertain the state is of individual particles. Because if it is alpha 0 plus beta 1 1, it will be mod alpha square 0, okay, 0 cat 0 bra plus mod beta square, bra cat.
So that's what
Yeah, right. So in some sense, as you say, even that top is also measuring some kind of uncertainty there also. But there are different types of uncertainty. Right. 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 Right, right, right. Exactly. Right, right,
Square of that or something.
right, right, right.
Or the,
And then, you see, some of the things can be, if you talk for a longer time, maybe one can understand things. I understand what exactly you have in your mind, and what is in my mind, I can explain. So, anybody else? Maybe I confused all of you, but yes.
just one second.
Yeah.
Regarding the fact about the fact that quantum fact not as immune to noise,
Yeah, yeah.
classical devices.
Right, right, right.
How do you think it's possible in
Mhm.
future, near or far,
Yeah.
for us to have more electronic or
Right.
quantum? Is that
Right. You have raised a real question, which is a real problem, right? That is noise, right? So because see, that's why we have realistic quantum computers, because because this uncertainty. Okay, this noise in the measurement process as well as system itself can whatever state it is, because of noise it decoheres after some time, right? So there are techniques of called this quantum error corrections, which people use to uh, correct errors which are introduced by this noise. But there is limit to it. That's why people say we may not have a useful quantum computers in next 2-3 decades. Why? Because this noise. Because people argue you may need maybe 1 million qubit to do to use Shor algorithm profitably. Because for each physical qubit to do error correction, you need many more qubits. So this becomes same thing in communication. Noise is a problem everywhere. Okay, but as you have seen, there are industrially certain communication devices are available, right? So they have controlled noise at least up to some extent, so that those devices are used, right? But you see, this is a big area now. This error corrections. Anybody who does anything quantum end up dealing with this noise. So that's why I said these things are very simple. So once you have a noise, you have a mixed state, then all kind of problems. So error correction is a very big area of research. See how to correct error introduced by this noise. This can change your state and also your measurement itself is noise. So all this, big area of research. Sure, sure. Right.
are there the path where we can
Yes. Right. I think in the quantum computing there is a theorem which tells you, which gives you certain limits that you have to achieve that limit on certain quantities. If you achieve that limit, then you can do profitable quantum computing. So for quantum, there is a theorem, but in each case, you can always find how much, what is the control that you need to do something useful. So like in teleportation, I know what makes it more useful compared to classical physics. Now noise is going to create problem. Now I can do, so this is actually another area. You have hundreds of papers in simple case of teleportation, how noise affects this probability as well as fidelity. Then if I want to have good fidelity, good probability, what should I do? How low should that noise be? Now noise can be also many different types, So given your particular experimental situation, one particular noise may be more creating more problem, how to control. But so there are numbers, and there are hundreds of papers for a particular situation, how much control you need on noise so that you can still do something profitable. Some protocol, like this teleportation is fidelity above certain amount. Only then you say this is success. Now question is, if there is a noise, it will degrade that fidelity. Now if noise is too much, you cannot do it. So how much noise is okay? That you can calculate. By introduce noise in your whole formulas, calculate the fidelity. Then you say that parameter which characterize noise, how low that should be, so that you still have large enough fidelity. So a lot of work is done in this in different areas. There are lots of papers on noise and how it is going to affect any. So you come up with any protocol. You start with pure state, but pure state is not something real in life. You put some noise, there are problems, then how to mitigate those problems. Then people try to compete. And one of the things that they do is error correction. I mean, like for classically, there is also error correction, right? But that is very well established. In your telephone also using error correcting tool, So there they work well, but quantum mechanically it is still, big area of it. Oh, yeah, I am.